All right, guys. So we're going to talk pressure testing. When I say pressure testing, I mean a pressure test after repair work or installation work of an HVAC system, refrigeration system, a heat pump, something like that. We got Julian Finbow, who's a serial writer for HVACknowitall.com. When I say serial writer, I mean he's written a few articles and he's going to write some more as well. So in this first part, this is a two-part podcast. In this first part, he's going to mention how leaking valves on a live system can really, it can trip you up if you're not cautious or not paying attention to it. So a live system, what is that? That's a system with refrigerant already in it, like you've pumped it down and isolated part of the system, and then you're pressure testing the other part. So that's going to be part of the conversation, guys, in part one. So let's get to it. This is the HVAC Know-It-All podcast. I'm your host, Gary McCreadie. This podcast is sponsored by Cool Air Products, Master, Cintas, and SupplyHouse.com. Go to the show notes and click on the links to check these guys out. All right, Julian, this is your first time on the HVAC Know-It-All podcast. Welcome, my man. How you doing?
Thanks very much for having me, Gary. I'm doing great. How are you doing today?
Awesome. So listen, you wrote an article for HVACknowitall.com. You've written more than one, and I'm glad to have you aboard to continue to write because your articles are in depth, they're well thought out, and they're educational. So the last one that you wrote that landed on the website was about pressure testing systems for refrigeration, air conditioning, HVAC in general. So that's the conversation we're going to have. So I'll give you the mic now and just kind of set us up, like the pressure testing. How important is it? Why do we do it? So on, so forth. And we'll get into this conversation.
Right on. Yeah, so pressure testing is an interesting one, compared to things like evacuation and charging that people generally think are more technical. It has its own place, and it's just as important as those considerations. So it might be something that you let an apprentice take a run at and try, especially on a smaller system if you're working with someone and they're apprenticing under you. But there's a lot of aspects to it where you can kind of gain efficiency by paying attention to them and following them. There's a lot of standard practices that are important to take a look at. And then there's a huge difference in smaller systems to larger systems, which is one of the things I cover in the writing you referenced. But there's also different stuff that I didn't mention, like pressure testing a live system when valves leak by, right? When there's an inspector watching you and there's a system with old valves and stuff like that. Different install components like flare nuts, traders, different types of valves, threads, packing on valves. So it's kind of a big world. So as simple as it is in a nutshell, it's a important topic.
Yeah, for sure. And it starts with a tank of nitrogen and a pressure regulator. Now, I'm going to give everybody a tip when it comes to your tank and your pressure reg. Now, there's tons of different pressure regs out there. There's many different kinds. There's pressure regs that will give you the option to flow, purge, and pressure test. There's pressure regs that'll just give you the option to fill a system up or regulate it how you like, right? So when you put your regulator on and you tighten it, what you want to do is you want to make sure that you're facing the regulator away from yourself or anything potentially that it could damage when you turn your tank on. Because if we're talking about a nitrogen tank, the traditional tank is around 2100 psi of pressure in there, right? And if you turn that tank on and your nitrogen reg is not sitting right or it's damaged and it flies off, you want it to fly off in a direction that's not going to hit anybody, and you want to be holding that tank stable and well because you don't want it taking off and becoming a projectile, right?
Yeah, absolutely. Like, as benign as it might seem, or I can compare it to oxygen, nitrogen does have its own dangers associated with it, right? It's not, in my opinion, as dangerous as oxygen because it doesn't have the innate ability to complete the fire triangle and cause an explosion. But yeah, like a loose hose can cause serious injury. I did work with a mechanic who, because of a loose hose during pressure testing, as everyone just thinks is a a safe thing. I mean, at a surface level with not as much dangers associated with it as like a live system. Wore a gash on his face permanently just from a hose that blew out because it was old. It wasn't going to carry refrigerant, but they do still need to function. And, you know, valve and bottle cap shearing is going to cause a projectile as well.
I had an instance similar. I wasn't pressure testing. I was using my nitrogen tank and a hose to blow out a drain line on a walk-in. No, sorry, I was standing on a walk-in cooler or freezer, and there was an air handler up there, and it was such a tight space. And I turned my reg on with my hand on the hose, cranking the reg up to a higher pressure, and my hand was on the hose inside of the drain, and somehow it let go out of my hand, and the thing just started. This is like a 6-inch hose. It started like waving and whacking around. It was hitting me in the legs, hit me in the nuts, I think. Well, but it hit me in the head, like right above my eye, like on more like the forehead area. And like if anybody has ever gotten hit on the corner of their head, just kind of above their eyebrow, that spot on your head,
Yeah.
it just bleeds really, really hard, right? Yeah. It just
Yeah.
bleeds hard. So I didn't even know I was bleeding. But after I was able to settle down the hose and come off the walk-in cooler, I come down and I'm in a kitchen, right, of this downtown Toronto restaurant, this kind of high-end restaurant, and it's in the kitchen in the back, and I got blood running down my face. I don't know. And the chef or the manager comes up to me. He's like, "Are you okay?" And I'm like, "Yeah, why?" He's like, "Well, your face
Yeah,
is
you don't look okay.
filled with blood."
Yeah.
Right? I thought I was sweating because it was so hot up there, but it was blood coming down my face. I didn't really see it. It must have been coming down the side of my face. So you got to be very careful when you're dealing with high pressured cylinders like nitrogen. And I know I wasn't pressure testing, but it's still a nitrogen tank. You still got a reg attached to it. You still have the potential of that high pressure getting loose somehow and causing havoc.
Yeah, absolutely.
Let's get into a little bit of pressure testing. So you talked about a live system. What did you mean by pressure testing a live system?
So retrofitting is one of the most interesting things to do in a trade. That's going up to a system and, let's say, fully repiping it or partially repiping it, maybe replacing a component. It could be something as simple as replacing a compressor. For efficiency and just simplicity, a lot of the times refrigerant is left in the system. So long that it has a receiver, no matter how small or big that it is. So just one that I referenced in the opening was on an ammonia system. We did a condenser swap over 1 day, which is a pretty good thing to do in 1 day. There's like, two guys on it for a day. So it's dark at night, it's like 8 p.m. or something at night. And we're just finishing the pressure test with the TSSA inspector, right? So this concluded like pumping down the high side of a food plant that had like, I think it's like maybe an 8,000 pound charge system. So moving that out. Yeah. And then just like cutting out a condenser, evaporative condenser, craning it off the roof, replacing it. And you got, 2 to 4 refrigerant connections. I think it was just 2 on this one, inlet and outlet of the condenser, and then a water connection. And then I'm pressure testing it, right? Because it's a system which you need the TSSA to witness. And what was happening is
The TSSA, just so I just want to mention we have a large audience in the US. So the TSSA is the local governing body for pressure vessels. So that's what Julian's talking about when he says the TSSA inspectors on the roof. They're our governing body for that specific and even gaseous fuels as well. So I just wanted to throw that in there so everybody knows what you're talking about.
Yeah, exactly. Thank you. So these globe valves, which are commonly used on ammonia systems, are like 40 years old, and from being wire drawn and probably maybe things getting stuck in them over time, they don't hold completely. They hold very well for an old valve, but when you pump that up to what they want to see, 250 psig of nitrogen, and the standing pressure of ammonia is like 100 psig, everything's turned off. Nitrogen's leaking by into the existing system. And there's only a couple welds, right, that we soaked, made clear that they are not leaking. The welder was a good welder who's on site. And it took him like an hour of, I don't know what, talking to get it through his head that, okay, you're leaking nitrogen into the system and this is holding. You can complete your pressure test and get the system back running, right?
This is a common issue in air conditioning and refrigeration. I've witnessed this quite a lot. It's actually quite common when, and I'm going to get away from pressure testing for a minute here. Let's say I'm changing a semi-hermetic compressor, and I've done this lots of times on like a Liebert system. You valve the compressor off because it's got a service valve on the suction side and on the discharge side. So you valve it off and isolate it from the system. You can unbolt the service valve from the compressor, unwire it, and pull the compressor out, put the new one in, and bolt it back together. Now, when pulling a vacuum, sometimes you're going to put that compressor into a vacuum, but if those valves are not holding, you're going to start drawing refrigerant out, and you'll never get to 500 microns or below it because the valves aren't holding. And I've been in this situation many times. Like, you can actually smell refrigerant coming out of the pump, and you're like, you know what? We've just basically removed the air and we're now purging that whole compressor with refrigerant. It's time to stop this evacuation because we're losing our charge and put it back into service. And you'll never get 500 microns out of that. So you always got to be careful when you're a live system that has refrigerant in it. Like you said, make sure that your pressure is not too high to move into the refrigerant side. Even guys in residential have brought this up, because some manufacturers out there want 400 or 500 psi of a pressure test, right? But if the standing pressure in that 410A condensing unit sitting outside is 150 psi, for instance, those valves aren't completely holding 100%. You're going to force nitrogen into the system, and now you got non-condensables in there. So it is a concern for sure. What do you think about the residential side when it comes to that, Julian?
Yeah, it's the same consideration, right? And despite valves on holding under positive pressure to lower positive pressure, what you brought up about pulling a vacuum is huge. And it can even be on a new system where you got nitrogen on one side and vacuum on the other. Because in compressor test stands and chillers, butterfly valves are used, which is not super common on refrigeration systems. So they're used in the refrigerant circuit. So on a chiller, they'll be used on the suction line because they're inexpensive for manufacturing and they do the job. They can be class 150 because the suction pressures are not very high. And there's a really low pressure drop through a butterfly valve. So compared to any other type of valve, a ball valve or a globe valve. And then on test stands, compressor test stands, it's common to use butterfly valves. So if you want to test if they're holding, because if you want to repeatedly pull a vacuum on a compressor and swap it out, like on a compressor test stand, you're going to have refrigerant pressure on one side of it, right? So in any scenario where you're pulling a vacuum and you have positive pressure on the opposite side, you can research it pretty heavily. There's not too many valves that are going to give you some literature in their manufacturing data and say that they'll hold. I would say aside from globe valves, they perform very well, the globe valve.
You can even encounter this with solenoid valves as well. Like on a pump down, you're going to pump down a system using a solenoid. Let's just take a typical system that's split. There's an evaporator, there's a condensing unit, and we have a solenoid valve in between. We close the solenoid valve, we pump the system down. If that solenoid valve is not holding 100%, and in my experience, solenoid valves don't hold very well at all. They have like a slow leak rate. A lot of them, slow is a relative term, so a lot of them leak by pretty quickly. Like if anybody out there, I'm going to go through two phrases, or I guess they're phrases: non-recycling pump down and recycling pump down. So If you're working on a recycling pump down system, the way it works is the solenoid closes, the system pumps down, it goes off on a low pressure switch. Okay. I think I have an article actually on that on hvacknowitall.com. Yeah, I think I'll post it up on the show notes here. Now, if you pump down, it goes off on low pressure. The way a recycling pump down works is that you have a leak in your solenoid valve, right? It's leaking by into the low side of the system. The low side of the system's got a low pressure switch with a differential on it. If it gets to the differential setting or the cut in setting, the compressor will start and it will pump that system back down again, always maintaining that pump down status. That's a recycling pump down. If the system is non-recycling pump down, it pumps down once and it doesn't pump down again. So if that solenoid is passing by, it's going to pass by. I guess the downside of that is now you could have liquid refrigerant migrating back to your compressor and you could start up with a liquid slug. So that's the only downfall to a non-recycling pump down over a recycling pump down. So anyway, let's get back to pressure testing. So the majority of this audience is not going to work on ammonia. And I know you're talking about an ammonia system that brought us into valves holding and all that, which is great. What about smaller systems? What about anything from 2 ton to 10 ton that is split? You're running pipe, you're running DX piping in between the two. How are we going to handle that? Because there's some companies out there that once they get a piping section done, and I've done this on VRF before, they will pressure test that section of pipe, right? So they know, okay, we're good there. We're good there. So when we pressure test the whole thing later and there is a leak, we know we're good there. And every sort of few days or how much line sets run, how many joints are brazed in, they'll pressure test that section and move on, right? That can be done, I guess, on smaller systems. Let's go to smaller systems first.
Yeah.
Give me your thoughts on pressure testing a smaller system.
So a smaller system, in general, you don't have as many problems just because of the less amount of joints of any type. But being diligent for the time that something does go wrong is definitely going to save you time, at least, and nitrogen, which is just expensive. So, like if you're going to do a ductless split or something like that, so that just would be a evaporator coil inside of a home, for example, run straight through the wall to a condensing unit outside. So with all your other components, compressor, metering device, and condenser, the usual spot you're going to have most of your tools is outside. So you would figure out which refrigerant you're using. The one that I referenced in the article is 134A, which is still a common refrigerant until things change a bit more. But you want to check out on that system what your saturated condensing temperature is. So your saturated condensing temperature is the temperature at which refrigerant will condense in your condenser. And it's kind of a weird thing to think about sometimes, but it has to do with the design of the equipment. So equipment is actually designed for certain areas and to have the temperature differential between the air on like a hot day in the summer in Arizona or Hamilton, Ontario, to the condenser operating. So if you use whichever SCT that system is going to run at, so air conditioning is like 120. Would you agree, Gary?
Can you repeat that? What's 120?
Like 120 Fahrenheit is a pretty common saturated condensing temperature for air conditioning.
Yeah, it's even lower now. It's even lower with the high efficiency appliances, like 100 even. 100.
Yeah, so you use 100 as an example as a saturated condensing temperature. Whichever refrigerant you have, you're going to look at your pressure temperature chart. So if you have any refrigerant and you take the saturated condensing temperature, go to your pressure temperature chart and reference the pressure. You could just use 200 PSIG as an example. If that's what you're condenser is going to run at when it's operating at design, you want to test a bit higher than that. So the number, which is standard from ASME, American Society of Mechanical Engineers, is 1.25 the maximum operating pressure. If you have a refrigerant that's going to run at 200 psig, and you multiply that by 1.25, it'll take you to 250 psig. So that gives you your target
So
for your pressure.
when you say so maximum operating pressure under normal conditions, because you could have a higher pressure with a dirty condenser type thing. When they say max operating pressure, do they mean under normal conditions?
Yeah.
Or could it be with a dirty condenser? Yeah.
Well, that, Gary, like you said, if you had an abnormal condition like a dirty condenser, the pressure in the system is going to run higher on the high side, but it shouldn't be approaching 1.25 times higher. It should still be within a range that's below that. So that's like a test pressure. You go higher than where it could get to under a poor condition.
So from what you said, we have 100 degrees Fahrenheit for 410A. Under normal conditions, that's probably what we'd see as a saturated condensing temperature. That relates to 317.6 psi, right? A lot of techs will pressure test to is 400 psi on a 410A system. So that sort of matches up to what you're saying. And that came from where? Where did that standard come from?
That's an ASME standard. So I don't know exactly where it's at in their literature or websites, but that was really common as soon as we started, doing documented pressure tests to use 1.25. And it was also common, as I mentioned, in the research and development field too, when you're manufacturing equipment.
Yeah. And I guess you have to keep in mind too, that and I used to see this on like R22 equipment all the time, like the evaporator was only designed for a certain pressure, but the condensing unit was designed for a different pressure. So when you're pressure testing, you have to be cautious of that, right? You don't want to go over the rating that the evaporator is supposed to be pressure tested at, or you could damage it. So that's something you have to keep in mind as well, right, Julian?
Yeah, and the other thing is funny enough that they're sold together. Like if you buy a dual pressure control for a commercial application, which is a high pressure cutout, and attached to it beside it is the low pressure cutout. So your high pressure cutout obviously is going to be rated high in its capacity, but you can actually have a low pressure cutout that it can only take like 150 psig of pressure, or you'll void the manufacturer's warranty. It could conceivably burst the bellows or weaken it and operate properly. So yeah, on the low side, you have to check that out before you apply pressure to it.
So something I want to bring up as well is the fact that when you're pressure testing, and I notice this with digital gauges the most because they're so sensitive. When you're pressure testing, a couple things. You need to let the pressure go in and equalize into a system, especially if it's a big system. Okay. If it's a big system, the pressure, you can slam it in 400 pounds PSI, and you need time for that pressure to equalize throughout the system to get by all the valves and go through all the cap lines and small sort of like orifices or wherever they could be within that system. So don't stare at the gauge going, it's dropping. Like, why is it dropping? Give it like time. It's hard to say how much time depending on how big the system is, but give it some time, let it sort of equalize out, and then start watching to see if it drops. And the other thing you have to keep in mind too is that depending on the day, if it's a cloudy day and you pressure test your system and the sun comes out of nowhere and it starts beating down, your pressure could rise a little bit, right? And if it's the opposite, if you pressure test on a hot day, the sun's beating down, a bunch of clouds come in, it starts to rain, and the temperature outside just plummets. Well, your pressure in that system could also start to drop a little bit and you think there's a leak. But there's tools out there, and there's like calculators out there. There's also tools that allow allow you to hook up a temp clamp to the pipe, and it calculates it for you within the digital gauges. I know the higher end Testo digital manifold has that capability as well.
Nice. That's sweet. So it has like the equivalent of that tool doing it manually built into that application. And
Yeah, yeah, you put it onto your pressure test mode, and you put the temp clamp onto the pipe, and it measures the pipe temp, and it calculates it all for you. So it's a very cool feature, and anybody that's using digital gauges and you see that decimal point, like you got 2 points to the right of your decimal, and you start seeing those drop, you're like, oh man, I got a leak. But not necessarily all the time you do. It's just it's a very sensitive apparatus, right?
yeah, absolutely.
So what else you got to throw in for as far as tips and tricks for pressure testing?
Yeah, so getting back to small systems, besides the stuff that we covered, it's just good to be thorough, right? Because if there's some kind of nuance that you don't catch, um, it's important after you apply the nitrogen to be thorough with it and spend the appropriate time. So besides going up, like we'll use for 410A saturated condensing temperature of 100 Fahrenheit multiplied by 1.25, it was equal out to 397, round up to 400. As a first step, adding nitrogen, you want to go up to half of your final test. So in really big systems, this can save you tons of time later. But for a small system, if it's a quiet work area, you'll be able to hear a leak at 200 psig. So if you start at the outdoor unit, which is traditionally where you add um, nitrogen or do most of the work on install like that, you can do a relatively quick soap of things and listen, right? So any kind of joint, braze joint, you have a flare joint, maybe you want to spend a little more time on the flare joint and be comfortable quickly that you don't have leaks. Do the same thing inside. At that point, you're going to bring yourself up to your final test pressure of 400 psig, where you also really should hear it if you have a leak. But that's the point where you want to be, start a clock for an hour, like I mentioned on smaller systems, and give yourself a thorough soap test of everything. Even if you're, good at brazing, you still need to give a good check to your braze joints. At least for inspection, you should always be doing that anyways. An inspection mirror and a flashlight are really good tools for a pressure test on any system. Save you a lot of time. You don't have to get into those weird spots. Then, if you're thorough and confident with the outdoor, inspect the indoor coil, whatever you can see on the indoor unit, piping. And then after that, it's waiting a period of an hour and then, ending your pressure test to blow the pressure off.